How about now? Can you hear me now, Kaylin?
Yes, I can.
Awesome, thanks. Cool. Here is the attendance form for everybody. Please do fill it out when you have a second. Also, as far as attendance goes, I did just update the attendance for everybody, so your current attendance should be accurate as far as everything you've filled out. Yeah. Okay, what are we doing today? What do you want to do? Let's see. I've got some review problems I will hand out to everybody. This review, you can all see on the screen as well. It is posted on Canvas and the solutions are as well. So certainly I can't imagine we would get through all of today. If you want to be able to look at the answers to other questions later on, or work on them first and look at the answers if you decide to take the final. Right, this is all predicated on if you decide to take the final, then here's some practice material. All right. So yeah. So if you decide to take the final, I should let you all know that there is drop-in tutoring on Sunday in the library from 3 to 7. What else? What else is important to let you know about? Solutions that are posted. We can go over any of the problems from this that you want to, if you want. I was just gonna pick some, but you are certainly welcome to type up and say what you'd like to see. For those of you on Zoom, if you want to go log into Canvas and look at the handout and select specific questions for me to go over, I'm certainly happy to do so. The other thing I wanted to mention was 2 things. One, on Canvas, there's a course evaluation link. Please fill it out when you have a chance. It's not super duper important, but it is important to me. It is anonymous. At some point, I will eventually get all of your feedback kind of aggregated and sent to me. I won't know who wrote what, but I will certainly see your comments and constructive criticism. So if you have things you want to say, please do let me know or fill out the thing. It is something we do look at every quarter. And the other thing was the Google registration form for the 16C workshop next quarter is live. So if you want to register for that, even if you can't come to the class at the time it's at, you can still be added to the Canvas and watch the videos later and all that kind of jazz. So you're certainly all welcome and encouraged to sign up if you want to. All right, but let's see. So someone just asked if we could go over some convergence divergence questions. Sure, so let's look at the ones that we have on here, which are all question 9. And then we can certainly make up some other ones if we need to. So let's look at this one. So does the following integral from 1 to infinity of e to the negative 1 over x over x squared dx converge or diverge? And I'm going to answer the question that I would usually ask, which is if it converges, find what it converges to. So converge or diverge. And if it converges, what does it converge to? All right. Personally, I like to do the integral without the limits of integration. So I know I'm going to do this eventually. I'm going to say that this is equal to the limit as b or t or whatever letter you like to use goes to infinity of 1 to b of e to the negative 1 over x squared dx. And then I'm going to actually do the integral. I'm going to do the integral on the side so I don't have to write all the limits of integration the whole time. So over here on the side, I'm going to do the integral of e to the negative 1 over x squared dx. And if we think about, if we think about what options we have, this is a mixture. It's an exponential and powers of x. It could be a u-sub or it could be an integration by parts, or maybe it could be something else. But it's probably one of those two. I'm always looking for a u-sub first. And my candidate for choice for you is the exponent of e here. U equal to negative 1 over x seems like a good candidate because it's in a place where we usually look for u to be. And also, more importantly, because its derivative, this is negative x to the negative 1, its derivative is positive x to the negative 2. Or in other words, 1 over x squared. So our du is equal to 1 over x squared times dx, which we exactly have right there. Or if you like doing it the other way, x squared times du is equal to dx. So we can totally rewrite this integral as the integral of e to the negative 1 over x squared times x squared du. The x squareds cancel. We replace the 1 over x with a u. So we get the integral of e to the u du, which is the best thing ever. It's e to the u. I don't need to write the plus c, but you could write the plus c if you really wanted to. And then that's going to equal e to the negative 1 over x. So that's what I'm going to get when I do this integral is e to the negative 1 over x. So then I go back over here and say, okay, this is equal to the limit as b goes to infinity of, well, the integral of this is e to the negative 1 over x evaluated from 1 to b. That is the way I would do that. I think it's the most kind of easiest way of not having to carry all this garbage with you through like 5 steps. And then we plug in, we get the limit as b goes to infinity of e to the negative 1 over b minus e to the negative 1 over 1. We let b go, we now actually take the limit, and sometimes this requires more effort than others. Here it's pretty straightforward. B goes to infinity, 1 over b goes to 0. So this is going to go to e to the 0 minus e to the negative 1. And you could leave your answer like that. You should probably simplify e to the 0 though. We should write this as 1 minus e to the negative 1, or I would probably write it as 1 minus 1 over e. So this integral converges to 1 minus 1 over e. Questions, comments, observations? I have to imagine if your teacher asks you, improper integral like this, improper, right? Yeah. That they will expect you to show your work in this way, where you write the limit of the thing, right? You need to, right, not just like plugging in infinity. So you need to be careful with your work for a problem like this. Someone asked, how do we know this e to the 0? So what we're doing there, this what we're looking at here. We're looking at problem 9a. So we know it's e to the 0 because we know that as b goes to infinity, sorry, well, pen, okay, come on, I can work a pen. As b is going to infinity, this 1 over b is going to 0 because you have 1 over a larger and larger number, which is getting smaller and smaller and smaller. That's how we do it. Cool, right on. Let's look at the next one. Unless there's any other questions about this one. But I really do, especially when you have a u substitution, you really don't want to like be trying to change these improper limits of integration. I don't want to figure out what, like, I don't want to rewrite this is x is infinity. I don't want to write that as like a 1 over infinity. That's not a good thing to do. So definitely with improper integrals, you typically do not want to change rate of integration. The next one is, I'm going to rewrite. So it's written as the integral from 1 to e of dx over x natural log of x. I would probably choose to rewrite it as the integral from 1 to e of 1 over x natural log of x dx. Now here's where we have to be a little extra careful. If they didn't tell you this one specifically was improper, you might miss it. It is improper though, because that integrand is undefined at 1. Natural log of 1 is 0, and you have division by 0 there. So we definitely have to write this as the limit as t approaches 1 of the integral from t to e of 1 over x natural log of x dx. And really, I should be approaching t from which side? Oh, sorry, approaching 1 from which side? From the right. Because we're between 1 and a bigger number. So we are on which side of 1? Oh, the bigger number side of 1. We are on the right side of 1. Always, whenever, if it's real numbers and not infinity or negative infinity, the lower limit you're always approaching from the right, and the upper limit you would always be approaching from the left, if that's the one you're replacing. All right, we're once again in a mixture situation, and I'm going to look for a u sub first. I'm going to hope for a u sub first, because I mean, not that integration by parts is terrible, but usually I think of a u sub being easier. So here I'm going to try letting u equal kind of the only thing that makes sense, the natural log of x. And that makes sense more because I can see its derivative is in there. That's also stuck somewhere, but like I can see du is 1 over x dx. And I've exactly got that. Again, doing it James's not favorite way. X times du is equal to dx. And so I guess I should be writing the integral here, maybe. That's a good idea. Yeah. So then I've got the integral of 1 over x, natural log of x times, instead of dx, we're going to write x times du. That x cancels with that x, and the natural log of u becomes 1. Sorry, becomes u, apologies. And then the integral of 1 over u is the natural log of the absolute value of u, which we then get the natural log of the natural log of x. Natural log of the absolute value of natural log of x. All right, so that's what this integral is equal to. So then we go back over here and deal with all the limit stuff. So we take the limit as t approaches 1 from the right. The integral of this we just said was the natural log of the absolute value of the natural log of x, evaluated from t to e. Then we plug in, and we get the limit. T goes to 1 from the right of the natural log of the natural log of e minus the natural log of the natural log of t. Whew, a lot of natural logs. So then here, natural log of e is 1, natural log of 1 is 0. So I might take 1, I usually probably wouldn't do this, but I'm gonna write this as the limit as t approaches 1 from the right of just negative natural log of the absolute value of the natural log of t. All right, so t is approaching 1. And what's the natural log of 1? Yeah, this is a place where I would say it's probably a good idea just to remind yourself how things are. I would really just draw a natural log graph. If I draw a natural log graph real quick, which has the point 1 comma 0. So if I plug in 1, natural log of 1 is 0. And then if I'm trying to take the natural log of 0, what's happening? Well, as the inputs get closer and closer to 0, my output gets more and more and more and more negative. Now, I should point out, is it James? Yeah, it is actually important here that we're approaching 1 from the right. No, I guess it's not. The absolute value takes care of it. It's fine. So yeah, anyway, the insides here are going to 0, and the natural log of something that's getting closer to 0 is getting more and more negative. It's getting infinitely negative. So we're going to get negative infinity, which is infinity. So this thing diverges. And if you're asked, we would say it diverges to infinity. Although typically on exams, I would say we usually don't ask how it's diverging. I could be wrong. Your teacher might ask you how something is diverging, but usually we just ask if it diverges, not if it diverges to infinity or to negative infinity or to, we can't tell. Questions? No. If you guys have questions, I can certainly address them. If you don't, it's all right. Or it's also fine to talk to each other about stuff. I just feel like top question. Okay. Let's look at the third one here. Oh yeah, the third one. Oh no, the third one. Ugh, okay. This looks terrible. Why does this look terrible to me? What is so terrible about this one compared to the other two? Right. This one, our place that's a challenge, our problem point, as I like to call it, is not 0 or 3, it's 1. And also technically -1 is -1, we're in the interval, right? If this interval goes from like negative, it would be really awful, then maybe break it up twice. But here, 1 is the problem. So we're going to rewrite this as the integral from 0 to 1 of 2x over, and yeah, I guess I'm going to write it like that. X squared minus 1 to the 4th dx plus the integral from 1 to 3 of 2x over x squared minus 1 to the 4th dx. And before I get too carried away, I'm going to do the integration right now. I'm going to do the oh my gosh, words. I'm going to do the indefinite integral before I do anything else. So the integral of 2x over x squared minus 1 to the 4th. Again, there's a really straightforward u substitution here. I should point out, this is not a partial fractions problem. You could try to do it like a partial fractions problem. You should not. Partial fractions is what I call a method of last resort or later resort. You want to try anything else first. So here, I would let u equal x squared minus 1, and du would be 2x times dx. So this is going to end up equaling the integral of du over u to the 4th, or the integral of u to the negative fourth du, which becomes u to the negative third over negative 3, or if you prefer, negative 1 over 3u cubed, which is negative 1 over 3 times x squared minus 1 cubed. Now, here's what's worth seeing here. When I see this, I can see that, okay, I'm gonna do my limit thing with one of these integrals, and I'm going to replace the one with something, and then do the integral, plug in my b, and then take the limit as b approaches 1. And I can see that when my b approaches 1 and I start plugging that in there, I'm gonna get division by 0. So I'm pretty confident here that this integral is going to diverge, meaning I only need to look at one piece and then I can say I'm done. So let's take a look. Let's look at this part here. So the integral from 0 to 1 of 2x over x squared minus 1 to the fourth dx is the limit as t approaches 1 from the left, because we are between 0 and 1, so we're smaller of 1. How do we know that 1 is the problem that we need? So good question. So the places that are problems for improper integrals are 1, any sort of infinity, positive or negative, and 2, any place where the function that we are integrating would be undefined that is in your interval. So this function here, 2x over x squared minus 1 to the fourth, is undefined if x equals positive 1 or negative 1. And since positive 1 is in the interval of integration, right? It's between 0 and 3. That's where we have to break it up. Negative 1 isn't in play because it's not in the interval. So wherever the function is undefined, if you're dealing with an improper integral, that's where you might have to either, well, that's what the problem point is. So if it's in between 0 and 3, you have to break it up there. If the integral was from 1 to 3, then we would just do the integral from 1 to 3, and we rewrite the 1 as a b or a t or whatever letter you like. Limit as t goes to infinity, t goes to 1 of the integral from 0 to t. Sorry, that's terrible. I know. Of 2x over x squared minus 1 to the fourth dx. Then we do the integral, which we already did. So we get negative 1 over 3 times x squared minus 1 cubed from 0 to t. We plug in the t into 0. We get the limit as t approaches 1 from the left of negative 1 over 3 times t squared minus 1 to the third minus negative 1 over 3 times 0 squared minus 1 to the third. And then we see that if we plug in 1 for t, the denominator here is 0. So you're dividing by 0, which means the whole fraction is blowing up. So this is diverging, and specifically it's diverging to positive infinity, because this denominator here, t is a number that's slightly smaller than 1. You're squaring it, it's getting even a little smaller because numbers less than 1 squared. Numbers between 0 and 1 squared get smaller, like 1/2 squared is 1/4. And then you're subtracting 1, which means it's slightly negative. You're keeping it so it's still negative. So then you're getting a very, very negative number, but then it's the negative of that very negative number. So it's a positive infinity. Also, another way you could justify this to yourself if you didn't want to say that is this function. If you graph this function, 2x over x squared minus 1 between 0 and 3, it's always non-negative. 2x is certainly positive between 0 or non-negative 0 to 3, and x squared minus 1 to the fourth is always positive in that interval as well. So you could see that this would always have, this would look like a function that has a vertical classical like this. Both parts are going to be positive here. So you could say it's infinity, what? Plus negative 1/3 if you really wanted to, but that's not important. It's just infinity. So this diverges. Now, technically, I should point out, to be able to say it diverges to infinity, which it does, you would have to do the other integral as well and say that so that they're both positive infinity. Because if this was infinity and this was negative infinity, we would say the whole thing diverges, but we don't know what it diverges to. But again, I don't think your teacher is going to ask you what it diverges to. So once one piece diverges, you're done. The whole thing diverges. All right. Welcome. And here's the attendance form, by the way. So, good times. What else? I think we should do a partial fractions problem. I would have to imagine if I was giving an exam and you haven't had, have you had partial fractions on the previous test? Yeah, I still feel like partial fractions is kind of a standard. test question. Partial fractions, yeah. I always want to say integration by parts part. Like they both have the word part in them, and it's just easy to say one when you mean the other. All right, so let's look at this first problem from this review. The integral of, I don't even know if it's partial. I don't know about that. Let's look at it anyway. Let's look at the first problem because it at least looks like it could be partial fractions, although I'm almost 100% sure it's not. And the reason I'm pretty sure it's not is because I can't factor that denominator nicely. X squared plus 6x plus 1 doesn't factor in a typical way. You could factor it, maybe. Yeah, you could factor it, but like your factors would be like x minus some terrible square root thing and x minus some other terrible square root thing, right? It doesn't factor in the usual sense. Although technically, I should just point out for your future knowledge, if someone asked you, does this factor? The answer is yes. I mean, but this one's not that awful. The factor is like this. So factor is not a great word. It does factor. It just factors in a not conventional way. What we really kind of mean when we're asking if something factors is, does it have real solutions? If you set this thing equal to 0, can you solve it and get real answers, or are your answers imaginary? If your answers are imaginary, then it really doesn't factor. If your answers are just irrational, then it still factors. Not too big a deal, but it just one point. So this thing doesn't factor in the usual partial fraction sense. But what should I even be doing before I even think about partial fractions? Even before that, although USEP is not a bad place to go. Like if this numerator was like 2x plus 6, I would definitely think of a USEP. But since my degree in the numerator is larger than or equal to, say it one more time. Yeah, and by simplify, we specifically mean we need to do the polynomial division. I will point out your teacher seems to like asking questions like this, like the integral of, I don't know what, x squared over x squared minus 9, and doing the polynomial division by just writing it as x squared minus 9 plus 9 over x squared minus 9, and then breaking it up as 1 plus 9 over x squared minus 9, and then doing partial fractions there. That's totally fine, but I would say this only works, this nice kind of simple way of doing it. It only really works in some special cases. I would say in general, you are always better off if you see a rational function and the degree on top is greater than or equal to the degree on the bottom, just do the polynomial division. Meaning, instead of doing this, even though this works here and it's pretty fast, I would do this instead. I would do x squared divided by x squared minus 9. It's pretty quick here too. X squared goes into x squared one time. 1 times x squared minus 9 is x squared minus 9. Subtract. That minus that's 0, and nothing here minus 9 is 9. Oh, look, this whole thing is equal to the quotient plus the remainder over the divisor. Same deal. I think you're better off doing this. Unless you're really, really comfortable seeing this. This only really works though when the degrees are the same. So that's what I would say. All right. So here, not so easy, right? You can't just add a little bit or subtract a little bit and see that, right? We actually have to like do the thing. So I'm going to do the polynomial division here. X cubed plus 6x squared plus 2x plus 3 divided by x squared plus 6x plus 1. You multiply x squared by x to get x cubed. X times 6x is 6. Oh, that's going to work out nicely. And x times 1 is x. Subtract 0, 0, 2x minus x is x plus 3. And so then we're going to rewrite this because I can't continue on, right? This power here is bigger than that power there. So I'm going to rewrite this as the integral of my quotient plus my remainder divided by my divisor. Now, someone could have made this. No, that's not true. Never mind. I'm going to say something that's not right. This problem is easier to avoid making a mistake at this point because you can't really do partial fractions here because you can't factor x squared plus 6x plus 1. But if I did this thing, it had like x squared plus 6x plus 8, which factors is x plus 4 times x plus 2. You might you might accidentally convince yourself that partial fractions was the way to go here. But before you do partial fractions at this step, you should check. Can I do a u sub on this simplified remaining fraction? And the answer here is yes, we can. If I let u equal x squared plus 6x plus 1, my du is 2x plus 6 dx. Or if I divide both sides by 2, du divided by 2 is exactly x plus 3 times dx. Or I'm sorry, I'm doing it the not usual way, but that's the way I like to do it. There's my du over 2 right there. So I should break this up into two integrals. It's the integral of x dx plus the integral of x plus 3 over x squared plus 6x plus 1. I guess I'll do it the other way. Du over 2 times x plus 3 is equal to dx. So this is du over 2 times x plus 3. The x plus 3's cancel. And then this is x squared over 2. Let's stop writing the integral of a thing we know how to integrate. Plus, this is going to be the integral of du over u. So we're going to get x squared over 2 plus the natural log of the absolute value of u plus c, which is x squared over 2 plus the natural log of the absolute value of x squared plus 6x plus 1.
Isn't it 1/2 times the integral?
It is. Thank you. Good call. I missed the 1/2 there. There. Yeah, there it is. You can see it, right? Yeah, maybe. Okay. So it doesn't happen often, but occasionally someone's going to write a problem like this because they don't want you to actually have to do the partial fractions, but they still want you to have to do the polynomial division. And they're going to make the second part, quote unquote, easier. And it is easier by making a u substitution instead of a partial fractions thing. So, something to look out for. Or more generally, after you do polynomial division, you should check, is this remaining rational function something I can do with a u sub? Again, all under the context of if you take the final. Yeah, let's see. Oh yeah, let's do this. So let's look at the next one here, which is the integral of x plus 2 over x cubed plus x squared dx. So certainly has all the hallmarks of a partial fractions problem. The degree on top is less than the degree on the bottom. Certainly not a u sub, because if I let u equal the bottom, it's not going to equal anything that relates to the top very nicely. And importantly, the denominator factors. So I'm going to rewrite this as the integral of x plus 2 over x squared times x plus 1. And I should point out, when I say the denominator factors, you should factor it fully. What I mean by this is if, for example, if we were doing something like the integral of, I don't know, 5x plus 1 over x to the 4th plus 8x cubed plus 16x squared, you can't just write it as, or when you're doing the partial fraction decomposition, you can't just write this as 5x plus 1 over like x squared times x squared plus 8x plus 16. You have to go one more step and fully factor it as much as you can. So this is 5x plus 1 over x squared times, this is x plus 4 times x plus 4. And actually, I should point out even further, you don't want to write it that way. Any repeated factor you want to write to a power. So you really need to write this as 5x plus 1 over x squared times x plus 4 quantity squared. So that then, let me ask you all, if I was going to do my partial fraction decomposition here, how many constants, A, B, C, etc., how many constants would I be having to, don't say the words, show me on your fingers or write it in the chat. How many constants would I be having to solve for? Yeah, it is 4. That is correct. It is 4 constants, right? We would have to do this as a over x plus b over x squared plus c over x plus 4 plus d over x plus 4 squared. I'll answer that question after we finish this problem here. But yes, that's a fair question. And well, maybe your classmates will actually answer it. So this one here, we're going to do our partial fraction decomposition. as a over x plus b over x squared plus c over x plus 1. And what I would encourage everyone to do is, I know it's kind of easy to forget exactly what's happening here. The easiest way to get to the next step is to just multiply everything by the denominator that you started out with, your common denominator. So I'm going to multiply everything by that. And you can write it the long way. I'm probably going to write it like this. I'm going to multiply this by x squared times x plus 1, and all of this by x squared times x plus 1. On the left, we're just going to get our numerator. The whole point of this is we should have no more denominators, right? When you do this, you should have no denominators. Multiplying this here, one of the x's cancels, and you get a times x plus 1. Multiplying this here, the x squareds cancel, you get b times x plus 1. Multiplying here, the x plus 1's cancel, you get c times x squared. Then we use our convenient values of x, which are going to be 0 and -1, because those are the values of x that make most of the terms go away. If you set x equal to 0, you get 0 plus 2 equal to a times 0. You don't need to write all this out. As soon as you see times 0, you're done with that. Here, I do need this one, b times 0 plus 1 plus c times 0 squared. That goes away. That goes away. I wouldn't even write those terms really, but I'm just showing you that everything but one thing's to be 0. So we get 2 equal to b. Great. Then we plug in x equal to -1. -1 plus 2 equal to a times -1 times 0 plus b times 0 plus c times -1 squared. So 1 is equal to c. And finally, we have one more term to find, a. And you can either, so I should say, if you have one thing left to find, you can just pick any other value of x you want. So if you really wanted to, I would pick x equal to the smallest thing that I haven't already picked. I would pick x equal to 1 and plug that in and find whatever a is by also plugging in what b and c are. So one way to do this is to say, pick any other value of x and plug in b equals 2 and c equals 1. So you're going to get 1 plus 2 on the left equal to a times 1 times 2 plus b, which is 2 times 1 plus 1 plus c, which is 1 times 1 squared. So I've got 3 equal to 2a plus 2 times 2 plus 1. So 3 minus 5 is -2 equal to 2a. So a is equal to -1. It's really only good though if you only have one thing left to find after you've exhausted all your nice values of x. The way I would usually go about doing this instead would be to equate coefficients. So if we equate coefficients, you look for the highest power of x on either side. But what's the highest power of x? Right, x squared. So on the left-hand side, I have 0x squared. On the right-hand side, if I multiplied it all out, I would have ax squared plus ax. I'd have bx plus b, and I'd have cx squared. So on the right-hand side, my x squared terms are ax squared plus cx squared, or a plus c x squared. Or in other words, the coefficients of x squared, 0 on the left, and a plus c on the right have to be equal to each other. That's why we'll call it equating coefficients. So if c equals 1, that means a has to be -1. Either way is totally legit, but I will say this second way of doing it is more typical people do, especially if you've got more than one thing to find. Like in the other in the example problem I just made up over here. Over here, if you were solving this one, you would use x equals 0 and x equals -4, and then you would still have two things left to find. And that's definitely when you would prefer to use equating coefficients. So then after you've done the partial fraction decomposition, don't forget to finish the problem, right? You've done all the hard part. The rest is doing the integral still. So we then have to say, all right, the integral of x plus 2 over x squared plus times, x squared times x plus 1, that's terrible. That's going to equal, I'm just going to look over here. It's the integral of, your teacher likes to have you do this thing where you like do the integral first. Yeah. That's fine, that's weird, whatever. I mean, right, I do get that. So okay, fine. Let's do the integral first. So anything that has the higher power, you want to rewrite that as to a negative power. So like a over x, I want to write as a over x. But b over x squared, I'm going to think of that as b times x to the minus 2. And c over x plus 1, I'm going to think of c over x plus 1. But like if I had a d over x plus 1 squared, I would write that as d times x plus 1 to the minus 2. Because higher powers don't get a logarithm, right? Their integral is not a logarithm, it's just in the reverse power rule. So here we're going to get a times the natural log of the absolute value of x plus b times x to the negative 1 over negative 1 plus c times the natural log of the absolute value of x plus 1. I don't love this because I want to write plus c. All right, plus k, I guess. And then first simplifying, a times natural log of the absolute value of x plus minus b over x plus c natural log of the absolute value of x plus 1. Okay, and then we can plug in our values for a, b, and c. So we've got negative 1, 2, and 1. So negative natural log of the absolute value of x minus 2 over x plus 1 times the natural log of the absolute value of x plus 1. Plus, I guess I'll still use k. That's what our answer would be. I don't think you need to do it this way, but if your teacher is encouraging you to do it that way, it's probably not a bad idea to do it that way if you take the final. All right, that said, somebody asked, what is the new final taking policy? I missed that. So I'll try to parse what everyone said, but you guys can correct me if I'm wrong. I believe the policy is you can, if you're happy with your current grade on the two, like your grade in the class based on your grade on the two midterms, just take that grade and not take the final. But since your second exam hasn't been graded yet, you have to take your actual exam that has been released back to you and grade it yourself as accurately as possible, and then calculate your current grade based on what that second exam grade would be. So after you do all that, you calculate what your grade would be, assuming you have done. And again, I would encourage you to undersell yourself a little bit, right? Definitely assume you might have gotten a little bit less than a little bit more, and then see what your grade would be. And if that grade is pleasing to you, then you can not take the final and take that grade. But you are basing that assumption on what you think you have gotten on the second exam. And yeah.
Something to add, which people were asking about, is she's not going to drop like the lowest grade. So if you take the final and you bad on it,
Right. Yes, the final, definitely taking the final is a risk, meaning that if you don't do well on it, it will count against you. It's not a free roll, right? You can't just take the final and not do well on it, unlike maybe in the past. Because definitely in previous quarters, in the more COVID-y times, there were people who were like having finals, and it was just like if it hurts your grade overwhelmingly, they would just drop it. So that is not the case anymore. I think that pretty much sums it up. Okay, hopefully that answers your question. So again, you got to calculate your grade on the second exam, or estimate your grade on the second exam, then estimate your grade in the class, and then decide if you want to risk taking the final to improve your grade and hopefully not lower your grade. All right. I know we've got 9 minutes left, but I think it's a call it a day kind of day. So let's call it a day. It's been lovely. I've really enjoyed having you all. It's been a lot of fun. Oh, do make sure, I did say, but let me say it again to be sure. Please do fill out the evaluation that's on Canvas for me. I will read those comments eventually, and it's good to know what I could be doing better and also to hear things I've done well. So please do that. My boss also does read them at some point. So I mean, be honest, say what you will, be nice, whatever. I care, but like, it's fine. I think we've had a pretty good class. I think you'll say nice things. I'm not worried about it at all, but please do fill it out, because it's the most important thing is actually having people fill it out. Yeah, good luck on your final. Wait, so the final is optional? Yeah, apparently the final is optional. I'm just learning this today as well, but the final is optional. But again, it is based on if your current grade in the class is satisfactory to you, you can opt not to take the final. There should be. So how did this all get communicated to you? In class? Okay, so maybe you haven't had your class yet, and she will say it in the afternoon class.
Yeah, no, she just sort of can't. Someone just asked her if she couldn't do it this way, and she was like, okay.
Ha! That's hilarious. Apparently someone asked in class, and she was like, sure, why not? Okay. So maybe if you missed it in your earlier class and you have nothing better to do until 5 o'clock today, you can wait around and go to the other one. I don't know. I wouldn't do that, but
And try requesting something else and seeing if you.
Right, yeah, maybe see if we can bargain for a better deal.
Final and.
Sure. In my experience, overall grade calculation, usually most grades get entered raw and they do a curve at the end. I could be wrong, maybe your teacher's doing something different, but that is often how people usually do things. Yeah. Yeah, of course.
I've been trying to sort of frantically grade myself.
Oh, sure. Oh, yeah. So maybe we shall so how you actually calculate your own grade. So let's talk about, we've got time. I mean, you don't have to leave, but yes. So if you were calculating your own grade, right? How much are your midterms worth? All right, well. I thought your question was. Oh, no. So basically you take your scores, you multiply them by the percentage they're worth. And then I guess if you wanted to calculate what you needed to get on the final, right? Like you would take your exam 1 score, multiply it by its percentage. Let's say it's worth 20%. And you take your exam 2 score. And you multiply it by, let's say it's also worth 20%. And you would take, I'm assuming you get credit for doing homework. You take your homework score, also multiply it by, let's say it's worth 20%. And then you take your unknown exam, your final score, multiply it by, let's say it's worth 40%, and set that equal to the grade that you want. And now solve for that. That's if you're taking the final, right? If you're not taking the final, this is how you're calculating your grade in your class.
Okay. So I did it the top way, and the answer is the bottom way. Are these equivalent?
It should be x plus 6 minus x squared, 0 to 3, 0 to 3. 3 to 5, 3 to 5, x squared minus x plus 6, x squared. Those should be the same.
Okay. Yeah, I thought so, but I don't know. I sort of broke it into extra steps, I guess.
Sure. Yeah. That's fine. Yeah. All right.
Thank you.
I was thinking the same. I was like, good. Yeah. I'm digging your outfit. All right. Have a lovely break. Good luck on your final. If you take it, good luck on your other finals that you actually have to take. And yeah, I look forward to seeing all or most of you next quarter. I mean, I look forward to seeing any of you that are going to be with me. I know some of you don't have to take 16C, but I definitely look forward to all of you who have to take 16C and will hopefully come see me. Of course. Yes. And I'm going to head over to CADS as usual if you want to get more help.
I mean, today.
Just a general idea of how to do a problem like.
Sure. So what I would actually say first is we definitely did talk a little bit about that last class. So if you want more about that, you could definitely go check out the video posted from class on November 30th. But the idea, so what are they asking you to do here? They're asking you to approximate an area using the midpoint rule.
Yeah, with 4 rectangles.